Bom dia a todos, bom dia nesse nosso terceiro dia, aliás, quarto dia, né, já de conferência. Hoje nós teremos o prazer de ter o professor Paolo Olivieri, né, falando um pouquinho sobre... eu perdi aqui o título da sua palestra, mas o professor Paolo, que está aqui, professor na Universidade de Gênova, na Itália, né? Paolo Olivieri fez mestrado em Medicinal Chemistry and Technology, seu doutorado em Science and Technologies of Chemistry and Materials na Universidade dos Estudos de Gênova, na Itália. Atualmente é professor assistente da Universidade de Gênova, no Departamento de Farmácia. Foi premiado o melhor professor, melhor jovem pesquisador na divisão de Química Analítica da Sociedade Italiana de Química, em 2010, e mais recentemente, agora em 2020, pelo Chemometric and Intelligent Laboratory Systems, né, o Chemolab Award, pela Elsevier. É vice-presidente da seção de Ligúria da Sociedade Italiana de Química, membro do Conselho da Divisão de Química Analítica da Sociedade Italiana de Química e coordenador do Grupo Divisional de Quimiometria. Também é membro do Comitê Permanente da Associação Internacional de Imagens Hiperespectrais, né, que é o IASIM, um congresso que, inclusive, foi adiado para o próximo ano, acho que vai ser na Dinamarca. É autor de mais de 70 artigos, 12 capítulos de livro, tem índice H igual a 24. A palestra do professor Paolo hoje vai ser em inglês, tá, pessoal? Mas se vocês quiserem fazer qualquer pergunta, vocês podem fazer a pergunta aqui em português, que a gente faz a tradução para ele, ou então a gente fala bem devagar, que ele diz que entende. Não, a gente faz a tradução. Então, good morning, Paulo. It's a pleasure to have you here. It's really nice for us to have someone like you speaking for the Chemometric, the Brazilian Chemometric Society, and please be much welcome, and you can start your talk. I will ask the guys to put your presentation, and well, the screen is yours.
Okay, thank you very much, Carol, for your very kind introduction. And I will try to share my screen now to visualize my presentation. Okay. Okay, it should work, I guess.
Yes, it's working.
Thank you. So first of all, I would like to thank the scientific committee and the organizers of this very, very nice and important conference. I was attending the session of yesterday, and it was very interesting with the very nice and interesting talks. So I'm very honored and pleased to be here, also virtually with you. I would have preferred to be there because here we have winter time now. We had snow very close to here yesterday, so we are in a cold period of the year here. So I would have preferred to be there, but these technologies allow us to be in contact also at a big distance with a very fancy way. So thanks to the organization and to the scientific committee for giving me this very important and nice opportunity to be with you today. And I will start now my talk, which will be about the chemometric tools that we use or that we should use to verify authenticity of a product. And we will talk a little bit about this during the talk. The chemometric tools that we should use to do that, to address that aim, are in the branch of qualitative supervised methods, and in more detail, they are the classification and the class modeling tools that we will describe in detail during this talk. But for now, we have to recall that we are in the qualitative supervised branch of chemometric methods, and as all the supervised methods, the classification and class modeling methods require validation. So we will make also a little focus on that afterwards. I have just said that we have two possibilities, discriminant classification and class modeling. And now we will shortly recall which are the differences between these two approaches that you know very well for sure. But just to recall this, we will do that with a very simple bivariate example with two classes, red and blue. Well, what the discriminant classification approach does is to build a delimiter, which is a mathematical function in the space of the descriptors, and this delimiter divides the space of our samples in as many subspaces as the classes are. So in this case, we have two classes and we have two subspaces for each of the two classes. So the delimiter is a mathematical function which is built taking into account information that comes from the two classes, not just from one of them. Instead, the class modeling approach is focused on a single class of interest. So you can build models for just one class of interest, and the mathematical function is an enclosed function that encloses the space of a specific class that we call the target class, the class that we want to model, in a closed way. So it defines a closed space in which samples of this class may fall in. Of course, if I am interested in more than one class, I can build the class model also for the other classes of interest. But the fact that the class modeling allows to build models just for one class is the reason for which it is also referred to as one-class classification. So one-class classification is something that we can do with class modeling methods, but that we cannot do with the discriminant classification method. So a first difference that we can see here is that with the class modeling approach, when we build models for two classes, for instance, we can have a region like that in which the two models overlap. So this is the first consequence. Another consequence, very clear here, is that if we have an outlier sample, the class modeling method is very good to identify this outlier, while the standard, at least the standard discriminant approach, the standard discriminant classification is not able to reveal that this green sample is an outlier. It will be classified according to the discriminant rule in the red class, because it is the class which is most probably the class of this sample, according to the discriminant rule. Well, this is the standard discriminant rule, but we also have the possibility of modify a little bit the standard discriminant approach, just introducing a minimum permitted distance and a maximum permitted distance from the delimiter. And so in this way, we can identify a sort of band which is around the delimiter, in which we classify the samples of the two classes. So in this case, I have an indecision region here around the delimiter, like in the class modeling case, and I am also able to detect and to identify the presence of outliers, like in this case, the two blue samples in these plots. But there is still a very, very important characteristic that makes this approach not a modeling one, but a discriminant one. And is the fact that the delimiter, so the mathematical function that we use to make classification, also in this case of the modified approach, is determined mathematically by taking into account the samples, the training samples of the two classes, so green and red. And it wouldn't be possible at all to define a delimiter just with samples, for instance, of the red class, while in the class modeling approach, you have this possibility. You can build the model for the red class just having only samples from the red class. And this is a very important point for the reasons that we will see now. Well, just to recall, the methods that we have in chemometrics are a lot for making discriminant analysis. Here you can see some of them: LDA, QDA, KNN, support vector machines, and so on. But maybe in the last 10, 15 years, the method that was mostly used by the community of applied chemometrics is PLSDA. And we will spend some words afterwards speaking about PLSDA to underline some properties of this method. But nowadays, if you make just a Google search or a Scopus search, you will find that PLSDA is the method most used for making classification. So these are the methods that we have in our box for making discriminant classification. Of course, there are others, but these are the main ones. And these are the methods that we have for class modeling. So the most famous are, I think, SIMCA and UNEC. Then there is the potential function method, which is a nonlinear method, very powerful, and other methods based also in this case on PLS. This is one class partial least squares, which was developed by a Chinese group, and PLSDM, partial least squares density modeling, which was developed by our group. And I will describe this method shortly at the end of this talk. So the most important and the most known, I think, methods are UNEC and SIMCA. UNEC was developed by Massart in the 80s, and it is basically an extension of T statistics to the multivariate space. So it is just a use of T-square Hotelling statistics to describe an elliptical class model in the multivariate space. Here it is represented in the two variables, so bivariate space. What we can see here is that we can have a different width of the model, and the width depends on the confidence level that we choose a priori, exactly as in the univariate tests based on student statistics. We can select a confidence interval, and according to the confidence interval, our model is larger or narrower. So this is UNEC, and this is SIMCA. SIMCA was introduced into chemometrics by Svante Vold, who can be considered the father of chemometrics, together with Bruce Kowalski, in the 70s, and it is based on PCA. So it is a PC model built with a PC computation made just on the class of interest, on the target class. And the statistics of the residuals is used with a Fisher statistics to define this class space around the model. And this has this particular shape. And this method, I think, is the most implemented in commercial toolbox for chemometrics. So maybe it is also the most known and used in the literature. So when to use discriminant methods and when to use class modeling methods? Well, discriminant methods are well defined and well applied when our problem that we have to study, we have to address, includes a definite number, 2 or more than 2, of classes which are well defined and that can be sampled in a representative and proper way. So in this case of this example, I had 2 classes of hazelnuts, which a producer roasted with 2 different methods. So method of roasting type A and type B. And this producer only had these 2 methods. So a third class was not possible in this case. His hazelnuts were only or class A or class B. In this case, so it was possible, in this case based on RGB image analysis data, after, this is a technical issue, segmentation of the background, applying just LDA, so linear discriminant analysis, a discriminant method, it was properly possible with an object-based approach to perfectly classify the two different types of roasting for these hazelnuts, so roasting A and roasting B. But what I want to remark now is that in this case, I had two classes which were meaningfully defined, and that it was possible to make a representative sampling for both of them. So in this case, it is appropriate to use discriminant analysis. The case is slightly different when we have to verify authenticity of a product. And in this case, in this slide, you see a lot of examples, for instance, of food products. And in the last decades, we had the consumer had an increased attention towards the authenticity of food, also related to the geographical origin. And this is perceived by the consumer as a sort of warranty of quality. Not always it is true, but often the consumer pays an added price when there is a specific label on the product that declares that that product was produced in a specific region. So we need methods to verify that. And not only in the food sample, in the food branch, also artworks are prone to counterfactions and other products that we use in the daily life, including the drugs. So we need methods to verify, of course, analytically, first of all, and then with chemometrics, the authenticity of a product. Methods and strategy that we use are basically an extension of hoteling concept of quality control. I have just mentioned hoteling before, speaking about UNEC. Well, we can say that all the class modeling methods are born with this reference of the work of hoteling on quality control. So we want to verify basically compliance of a specific sample with a model that is the model of the good samples, of the target samples, the right type for that class. And this is nothing than an extension, as we have already mentioned, of the student's concept of quality control in the univariate case. So we are in that field exactly. So why for authenticity studies discriminant analysis is not very good? It's not a very good choice. It's a biased choice. Because using discriminant analysis for verifying authenticity of, for instance, a wine bottle, it would mean that we don't know where this wine was produced, and we have just, for instance, these three possibilities. And we are sure that this unknown wine was produced in one of these regions here, and not in a fourth or in a fifth one, for instance. So very rarely we are in this situation, because we cannot know in which region exactly the wine that we have to verify was produced. So the real authenticity verification case is not this one. It's better this one. I go to the supermarket, for instance, and I don't find there a bottle with a question mark on the label. I find a bottle that declares a specific origin, for instance, in this case, Serra Gaúcha. And what I want to verify if what is declared on the label, Serra Gaúcha as the origin in this case, is true or false. And in this case, so from the chemometric point of view, it corresponds to verify if a sample falls within or outside an enclosed model, which is defined by class modeling methods, as we told before. So this would be the right way, from a chemometric point of view, to address the authenticity verification problem. Is this product genuine, right? Yes or not? And if it is not, I'm not interested in to know where it was produced. It is sold with a false declaration. So it is from also a legal point of view, it is a fraud. So I'm not interested into the real origin. I just say that it is a fraudulent, a counterfeit product. Well, in many cases, if you see the literature of authenticity studies, you see that in most of the papers, this problem is addressed with a discriminant method, defining two classes, one of which is the target class, in this case, Sergausha, and in the other class is all the rest of the world. So it would be all the wines, in this case, produced outside this very specific region. Of course, it is possible to build a model, a discriminant model, if you have these two classes with a sample set and analytical measurements taken on those samples. But there is a big problem in this strategy that makes this strategy really and heavily biased. And this problem is that the non-target class, the non-Sergausha class, in our example, doesn't respect the definition of class. A class is a number of individuals, persons, things, samples, that form a group because they are characterized by common attributes or common characteristics or common qualities or common traits. And so the question is, in our example, which attribute or characteristic or quality or trait do our non-target samples, non-Sergausha, have in common? Nothing. They are just produced outside that region, but this is not a property, this is a non-property. So from also a philosophical point of view, it wouldn't be correct to apply a discriminant approach in this way, so defining two classes, target class and non-target class. But the problem is not just philosophical. There is a very practical and chemometric problem behind this biased approach. And I will try to show you the problem with this simulated example. In this case, we have a target class represented in green, let's say the Sergausha wine that we mentioned in the example before. And this is a meaningful class sampled in a proper way. And for that class, we have built a class model with the UNEC method. So it is an elliptical class space based on the Hotelling square T statistics. Then I have sampled in a non-representative way, because it is not possible to collect samples which are representative of all the wines produced around of the world outside the Sergausha region. From a practical point of view, it is not feasible, it's not possible. So the non-target samples that I have collected are biased by definition, and with these samples and the green samples, I have applied a discriminant method, quadratic discriminant analysis, and I have built this delimiter. So now I hope that the animated figure will work also with the internet connection, and I will show you what happens if I change a little bit the composition of the non-target class sample set. So I will start now the animation, and as I hope you can see, by changing a little bit, I will repeat that, by changing a little bit the composition of the non-target class, the limiter of discriminant analysis is strongly affected, while the class model of UNEC, of class modeling method, is not affected. So the consequence of that is that I can build my model for the Serra-Gaúcha wine, for instance, by having just a representative sample set of the target class. I can forget about other samples to build this model. And I obtain, in this way, a non-biased model for my class. Well, so after that, we may expect that if we make a literature search on this topic, we find that the food, or in general, the authenticity verification is made mainly by class modeling methods. But here comes out a surprise. If we go to, for instance, to Scopus, and we made this work last year for writing the second edition of our chapter in the comprehensive chemometrics book on food applications of chemometrics. And if you go into the Scopus database and you type food authenticity and chemometrics, you find out something strange. More than 1/2 of the studies are made with discriminant methods. And just a small piece of the cake is dedicated to the class modeling approach. And we have examined for this literature review more than 1,000 papers of the last 10 years. So it is recent literature. So why this? Why there is this sort of rejection by the chemometric, applied chemometrics for at least community towards class modeling approaches? Well, the explanation is maybe complex, but we found out one simple explanation that maybe is not the only one, but it is a piece of the truth, is that it is a sort of bad cycle that underwent in this field during the last decades. So what happened is that class modeling methods came out later than discriminant methods. So few users were using them at the beginning, and they were implemented in very, very poorly in the commercial software. And so users, applied users, didn't find them in the software, and the use was even more reduced. And so software producers, seeing that in the literature cases, these methods are not so used, don't want to implement them so much in their packages. So users have a few of them available, and they use a few of them in their studies. And this is a bad cycle that maybe is one of the explanations for the reason, for the fact that class modeling is few used in the field in which it should be used a lot. Well, another trend of the last years is the use of a sort of modified discriminant approach to make what is called a one-class classification in this case. So this is one of the first examples of this strategy, and it was applied by using as the classification method the random forests algorithms. And the strategy is very simple. They take the target class, sampled in a representative way, and then they generate artificially a sort of cloud of outliers, we can see them here, around the target class. And so they have two classes, a target class which is representative and sample on real samples representative, and a sort of artificial non-target class generated in a random way. but with a very high number of samples. So they say it is representative of all the possibilities of non-compliant, non-target samples. And then at the end, they apply a non-linear method, discriminant, in this case, random forest. Well, we have tried to do something similar. So we have taken a target class, here represented in blue, and we have generated 300 of outliers in the PC space. And we have applied a non-linear method also in this case KNN, and we have obtained these classification results for our situation. Well, it is fine, but still the results we can demonstrate that depend on the composition of the non-target class. Of course, if I generate a very big non-target class, I minimize this effect, but the effect is still present. So if I try to generate different, of course, artificially and randomly different non-target classes and non-target samples, I obtain, by applying the same method with the same parameters, slightly different results. And as you can see also here, if I change a little bit the composition of the non-target class, also in this case, so it is not totally independent from the composition of the non-target class. So we can make what we can call something that tends to a one-class classification, but it's not a pure one-class classification in this case. Well, just to recall some important and basic aspects on the evaluation parameters or figures of merits. For class modeling, we have basically three parameters. Sensitivity, which is the rate of true positives, specificity, which is the rate of true negatives, and a sort of global parameter, which is efficiency, usually computed as the geometrical mean of sensitivity and specificity. Well, for evaluating sensitivity, I just need samples from the target class. So true positives can be evaluated just with sample from belonging to the target class. But to evaluate true negatives, so specificity, I need samples, objects from different categories, from different classes. So here arises a problem that we will discuss shortly later on. And another point is that, very important, that sensitivity is a sort of experimental measure of the confidence level that I set a priori for my model, for my class model. And also this aspect we will recall, we will focus on that later on. So take this slide in mind and these concepts in mind. So for evaluating the performance of my model, I can use also the ROC curves that I have seen mentioned in several talks yesterday. So this is a classical application of ROC curves for a discriminant case. What I do for building the curve is to move the delimiter from lower values to higher values of my variable, and to put in this plot the true positive rate and the false positive rate. And I obtain this curve that in this case is a very good curve when it tends to the upper left corner, is a very good situation. And on the contrary, like in this case, when the two classes are overlapped, the curve tends to the diagonal of this plot, and it indicates a bad situation, a bad separation in this case. But this is for discriminant analysis. Well, in our group, we proposed several years ago a strategy, very simple, to determine the ROC curve also for class modeling. And I will show in this example. I hope that animation is properly transmitted by internet connection. And you should see here a unique model that in this case, for instance, here that the best performing
Bom dia, pessoal. A gente está tendo alguns problemas técnicos com a conexão do professor Paolo, mas brevemente ele deve voltar. Vamos aqui tentar resolver, tá certo? Um pouquinho de paciência que a gente já volta, tá bom? Essas coisas são comuns na nossa vida remota, né? Já já ele deve voltar, só um momento.
Can you see me now?
Yes.
Okay.
Now, yeah. Yeah.
Made some problem in this case, so I hope
It happens.
temporary problem.
Yeah,
Okay.
but it was in the. We could see your the animation of the UNEC and the rock cube that you were building. So
okay, I will go there. So
yeah, okay.
For this,
yeah, the guys are going to put your screen as soon as you share it, and
okay, it should be on. No, share screen. Okay. Can you see the screen now? Okay.
Yes.
Good.
Perfect. Yeah.
Okay, we were basically here. Yeah,
I think, there. Yeah, exactly.
Okay, so after building the curve, what you can do. Thank you. And sorry for that. What you can do is to compare different outcomes from different methods. So to see, in this case, for instance, that the potential function method was the best performing for this specific set of data. So it is a good way to use ROC curves also for class modeling approaches. Good. So another important point is that when you have to optimize parameters in your model, so for instance, the selection of variables, the pre-processing or specific parameters like the number of principal components or latent variables if the method is based on PCA or PLS, or other parameters like, for instance, smoothing for coefficients or something like that. What you can do is to try, of course, with an automatic script, all the combinations of these levels of these parameters, and then you can evaluate the outcomes of this trial on a set of samples that we can call optimization sample set. But this is a very powerful strategy, but dangerous because it is very prone to overfitting. So afterwards, you have to validate very carefully your model with possibly with an external data set. But what you can do at the end is to report the results of all these trials in a plot in which you represent every model as a point, as a scatter point, as a function of specificity and sensitivity. So every point here is a model, and you can evaluate here the sensitivity and specificity of that model. And the nice thing is that you can also use colors to visualize the levels, the different levels of our parameters on our model. So, for instance, if this is the number of principal components, I can see how specificity increases when, but sensitivity decreases when I enlarge the number of principal components, for instance. So it is a sort of diagnostic tool for our models, not only optimization tool, but also a sort of diagnostic tool. And at the end, I can use simply the Pareto optimality criterion to select the optimal models according to the best sensitivity or specificity. And this, of course, depends on the specific problem that you analyze. Well, but doing that, we have to take in mind that when we use specificity to evaluate a model, when we use specificity, we are using samples from non-target classes. So we are making a choice. We are selecting the best model according to information that comes from the spurious, the non-target class. And so in this case, my choice can be affected, biased by that. So to overcome this problem, some years ago with the Russian guys, Oksana and Alexei, we have proposed a rigorous, what we call the rigorous strategy to optimize models of class modeling type by using just sensitivity. And how can we do that? Not just maximizing sensitivity, because I would have the risk of getting bad models according to the specificity in that case. Recall what I showed you before, that sensitivity is an experimental measure of confidence level. So I can choose the model that provides me with the sensitivity, the experimental sensitivity, which is closest to the theoretical confidence level for that model that I set it at the beginning. So if I set it, for instance, 95% confidence level, I will choose as the best model, as the optimal model, the one that provides me the sensitivity value experimental, which is the closest one to 95%. And in this way, I will select my optimal model just taking into account the samples of the target class. So it is a rigorous, let's say, strategy for class modeling and class modeling optimization. Well, we mentioned before PLSDA, and two more things about this method, which is very, very used, as we told already before. First thing, it is not a class modeling method. The DA letters in the acronym means discriminant analysis. So it should be clear that it is a pure discriminant method. Also, in the literature, you can find papers in which it is claimed that they made class modeling using PLSDA, and this is not possible by definition. This is a discriminant method. And I can tell you that there is a very, very nice tutorial paper written by Richard Brereton on this topic, partial least squares discriminant analysis, so PLSDA, taking the magic away. And Richard is very good at describing what is not very good in PLSDA method. But basically what we can recall shortly here is that for a two-class problem, it is possible easily to demonstrate that the solution provided by PLSDA is basically the same solution that LDA provides you. So it is not so advantageous. There is not an advantage in using this method for two-class problems. Of course, you can use LDA on principal components if you have a large number of variables, of predictors. The thing is different in case of three classes or more than three classes, because in this case, the solutions are different. And I let you judging by yourself, in this case, particular, if the solution of PLSDA is better or not than the one provided by LDA. But in any case, we must recall that for two class problems, PLSDA is basically the same as LDA. But the most important thing is that it is a pure discriminant method. So if we want to use PLS, because it is common, you can use PLS directly on your data matrix, also in the case in which you have a high number of variables and a small number of samples. If we want to use PLS to make class modeling, we have some approaches possible. One is the OCPLS method developed by the Chinese group that I mentioned before. And the other one is the PLSDM, PLS density modeling method that we developed some years ago in our group with a collaboration with the group of Itziar Ruiz Sanchez from the University of Tarragona in Spain. And this method basically is based on a PLS regression in which the response is a sort of density function computed in the space of the predictor. So the higher the density, the smallest, in this case, the value of this function, but you can change the sign of this function if you want a higher value for indicating higher density. So this is the response that you use, and this is computed just with the target class samples. So it is pure class modeling approach because it doesn't require non-target samples to develop the model. And how is the model developed? Well, you make the PLS regression using the original data, in this case, for instance, NIR spectra, and the density function in the predictor space as the response. And then you compute PLS latent variables, and you use the scores of the samples, the target class samples. And on these scores, you compute a model by using a potential function method that are non-linear class modeling method that you can use in this case in the space of the latent variable score. And we use these statistics related to the probability density that these methods use, together with the statistics of the residuals, like in the SIMCA approach, to build an evaluation of compliance of our test samples with the class model. So it is a class modeling for that, and it is a class modeling also because it is based just on the target class samples used to build the model. Here, just an example of application. We applied this in the first application for identify the authenticity of a product from our region, olives in brine. And we had a first sampling harvest made in 2 years, year 1 and year 2. We divided these this sample set into 2 subsets, a training set and a test set. The target class is Tajasca. Tajasca is the variety of olive from our region. And we have also non-Tajasca samples used to evaluate specificity at the end. So we have these 2 sample sets, training set and test set. And we also have what we can call an external test set from a different crop year, year 3. Also, in this case, we have target samples, Tajascan, and non-target samples, non-Tajasca, that we can use to evaluate our model. We have optimized the model in cross-validation, so inner optimization, optimizing different parameters. First of all, the number of latent variables, and then other parameters, the processing, and other parameters that are typical of this method. I don't go in the details, but L, A, and K are parameters of the method. Well, we can see here the results, as I showed you before, a scatter plot in the space of specificity and sensitivity computed in cross-validation. And each point here is a model that we have computed optimizing the values of these parameters. And it is nice, in this case, if, well, of course, I can see here which is the best model according to the Pareto optimality criterion. So I use this for selecting the optimal model, but I can also use this for a diagnostic evaluation, seeing with just with a color scale how the models change their performance according to the value of my parameters. For instance, parameter K, parameter A, and it is interesting, for instance, here to see the effect of preprocessing, and from the blue to the red color, N means no preprocessing, so raw data, and we move to mean centering, scaling, and column auto-scaling, the red A here. So we can see nicely that the effect of scaling data is an increase of sensitivity, a significant increase of sensitivity, and a slight decrease of specificity, as it could be expected. So it is nice because you have here also a diagnostic possibility to understand how your model behaves when you change parameters. So these were the modeling results. In this case, our method performed better than the traditional ones, Simcan and UNEC. So, to resume the key points of this long talk, the first thing important that we have seen this morning is that to address the authenticity verification problem, the most appropriate method is the class modeling approach. So this is the first important point. Then we have seen how we can use the ROC curves to compare models and also to compare methods on the same data set, of course. And we have seen how we can use Pareto optimality to select the best model when we tune some parameter in our modeling approach, and how this approach can be used also for a diagnostic evaluation of my model performances. Then we have also told that if I want to make a pure optimization of my models, I should use only sensitivity and not specificity. So it is the rigorous approach that we propose to optimize models in a rigorous way. And finally, we have shortly presented the possibility of using PLS not to make discriminant analysis like in the most common and most known method, which is PLSDA, but to make class modeling with the PLS-DM method that we developed some years ago. Well, to conclude, here you can see the current composition, well, not actually the current, we may say current composition with a ±1 confidence interval, but it's almost the current composition of our group, and to see in detail the topics on which we work, you can see this, have a look to this very recent article, which was published on NIR News last July. So here you will have a detailed description of what we make in the field of spectroscopy, in the field of authenticity verification, chemometrics, hyperspectral imaging, and so on. And so this is the picture. I perfectly know what you are thinking about the picture, because we wanted to take a better one, but then with the COVID restrictions, we hadn't until now the possibility to do that, but we will do that soon, I hope. But more important than the picture is that we organize every year in Genova a chemometric school, which is made 2 times a year in Italian, so national version, and 2 times a year in English, so international version. And there are 2 modules, one dedicated to multivariate data analysis and one dedicated to experimental design, so multivariate design of experiments. And the interesting maybe thing this year is that due to the restrictions, we are making this school online, so from remote, and so for maybe some of you that maybe want to participate in the online version. Well, you don't have the possibility to visit Genova, but you don't have to have the costs for the travel, for the staying in Genova, and so on. So for more information on that, you have the web link here and the QR code to our website with all the details on our schools. And just to show you where we are located, we are in the northern part of Italy on the coast. Genova is a city on the sea with a big port. And the bottom right picture specifically was taken very close to our department in Bocca d'Assa, which is a very small part of Genova, very close to our department. So we invite you to visit us. We are very open, of course, not in this period, but generally we are very open to exchanges, scientific exchanges. So you are, if you are interested in our work and in visiting our city, you can just write us, and we will be very happy to host you. And that's all. Thank you very much for your kind attention, especially at this time in the morning for you, which is very early. And so thank you very much for supporting me in this hour. And sorry again for the technical inconvenience. Thank you.
Thank you, Paolo, very much for your talk. It was not long. It was really nice to hear you. And I really hope the Brazilian government take vaccines seriously so we can go to Genova soon. We have some questions here. First, I will ask the guys to put Ricardo Saldanha's question. Yes. Ricardo is asking, I believe that 1 or 2 class models are very interesting as screening techniques in problems where little is known about the sample, such as in forensic field. Could you comment a little bit about that? What's your opinion?
Yes, this is a very important point. Thank you very much, Ricardo, for pointing out that. Exactly. One of the problems with the class modeling method, as we saw, is that there is the overlap region that in many cases is not well accepted by people. But using them as a screening strategy is a very clever way to overcome this problem, because you can use class modeling as a screening tool, and in the forensic field, it should be an ideal choice, this one. And in this way, you can identify very clearly the samples that are compliant with the target class, also which are not compliant with the target class. And so with this screening, you have analyzed, let's say, most of the samples that you have to analyze in the routine practice. And with the few samples that will fall within the undecision region, you will have the possibility to make further studies, and maybe also to apply different methods and also different analysis to go more in depth into that. But using class modeling as a screening is a very clever way to address this problem. So yes, thank you, Ricardo, for pointing the point.
Ricardo is a police expert, so Fernanda Honorato is asking what has been the acceptance of pattern recognition techniques by agencies that verify authenticity?
Another very good point, and the answer is thank you, Fernanda, for the question. Is not very well accepted at the beginning, because if they look in the literature, they don't find a lot of examples of application, as we saw, of these techniques. But especially in the case of class modeling, there are few examples. But I can bring you an example of a case study, the case study specifically of Tajasca olive that I have presented in the talk, was made with an Italian regulatory agency, which is Camera di Commercio called, and it is an agency devoted to verification of products on the market. And the nice thing was that this method was accepted officially by the Italian institution which is responsible for certifying the validity of analytical methods, and it is called Accredia, so it is an accreditation institute. And this was nice because this was the unique, until now, but the first and unique example of acceptance of these techniques by an institutional agency in Italy, at least in Italy. So it was 2014, and I think that nowadays it is still the unique example of officially accepted method for verifying authenticity of a very specific product, of course. But it was a first success that I hope will have a long series of other successes. Thank you.
Okay, we have another question from Aline Fonseca. Excellent presentation. To use PLSDM, do we have a better performance when we use more non-target samples than the target ones? One example, if you have more non-Tajasca samples, is that relevant to build the model?
Okay, thank you very much for the question. In this case, the answer is no, because being actually a real one-class modeling approach, it is not affected at all by non-target samples. So non-target samples that you saw in the training set actually were not used to build the model. They were used just to verify specificity of the model afterwards. So after that, the model was built. So it is not affecting the number of non-target samples, is not affecting the model. And this is the case for PLSDM because it is a real class modeling approach. Of course, if you use PLSDA, which is a discriminant approach, the number and the representativeness of non-target samples strongly affect the shape of the delimiter and the performance of the model.
Okay, and the last question from Professor Paulo Henrique Março. Professor, thanks for your presentation. I will divide my question into the characters allowed in the system. In metabolomics, it is very common to use few samples. Then after discrimination, the VIP scores are generally used to search for the reasons addressed to the difference between classes. Which is the most appropriate tool in this situation?
Well, thank you for this question. I am not an expert of that field, but of course, you can use modeling approaches also in this case, especially when you have to characterize a very specific class with a limited number of samples. But of course, if they are too limited, this may affect the characteristics of the models and also its performance. So having a sufficient number of representative samples is always a key point, at least for the target class. The VIP scores are a possibility that you have in PLS to evaluate the role of original variables in the model. And of course, we can implement this approach also in PLSDM. So to take, to recover this information of how the original variables contribute to the performance of the model. So for this type of diagnostics, of course, also in this case, it is possible to have this information. It's a bit more complex to get this, but it can be implemented. Actually, it is not implemented in the current version of the method that we have in MATLAB, but it can be implemented easily. So if someone is interested, we can do that. Thank you.
Okay. Okay, so for now, we are going to close the question session, but if anyone has other questions, they can send to us and we can send it to you. We have many compliments for your lecture here, Paolo, so you can check the comments as well. later. If you have any final comments, if you want to say anything.
Well, just to thank you again for this very, very nice conference, and to hope to meet you in person soon somewhere.
Yeah.
Next year we will organize the CAC in Europe. We are not sure for right now, but we will see. So I hope to see all of you soon somewhere. Okay, thank you again.
I hope so too. Okay, so thank you very much, everyone, and I hope we meet you all in the next conference that it's going to be in another link. Okay, bye,
Yes.
Paolo. Thank you again.
Oh,
Have
bye.
a nice day. Ciao.
Ciao.